हेलो, आवाज़ भी आ रही है? चेक।
Cover me!
Team match. Let's go.
The blue team has scored for the first time.
Team match. Let's go.
Watch out. Cover me! Watch out.
जानू, तुम्हें एक URL मैसेज कर रहा हूँ, देखो चल रहा है?
Reloading! The blue
स्क्रीन पे करो जरा, बताओ सही चल रहा है? आवाज वगैरह देखो आ रही है? हाँ? चल रहा है? ये करो।
Watch out!
फुल पे करो, फुल पे।
Half of the match is over, and the blue team is in the lead. Mark the location. Dead! Reloading! Killed! No mercy! Cover me! Killing spree for the blue team!
Great. You're about to win.
The blue team is about to win.
Blue team victory.
बस ये दो, वहाँ से बंद कर दो, वहाँ से बंद कर दो, वहाँ से बंद कर दो। हंस क्या रहे हो?
Team match. Let's go.
First point. Reloading! Cover me! Killing spree for the red team. The red team is in the lead.
तो इसकी आवाज आ रही है इसमें।
Reloading! Killing spree for the red team. Enemy down! Cover me!
Be careful. You're losing the game.
The red team is heading to a perfect win. Clear! Reloading!
Red team victory.
जानू लैपटॉप दे अपनी चार्ज हो रहा है ऑन करो इसे। इसके स्टैट्स देखो भाई लोग ऑन करो इसे। इसकी ऐसी की तैसी, मेरा नोटिफिकेशन पैनल क्यों खुल रहा है बार बार? No, all
Team match. Let's go.
The blue team has scored for the first time. No mercy.
आतंक आगे बात चले गया आतंक वो आतंक बोल पहुंच रहे नवाज आ गया नवाज
Clear. for the red team.
Ready, Maddie? रेडी कर, आतंक रेडी कर.
हाँ
Bring up voice chat.
बस साथ में हो गया.
Bring up voice chat. Bring up voice chat.
So we talked about MapReduce at a conceptual level, what mappers and reducers do, and it's really not that complicated, is it? So let's talk about a little bit more depth about what's actually going on under the hood when you run a MapReduce job on a Hadoop cluster. So let's go back to that example that we used in the previous lecture. Again, we started off with a bunch of movie ratings data. Our mapper extracted that into key value pairs. And then our shuffle and sort operation organized all the values associated with each unique key, which then got fed to our reducer to produce our final output. So what's actually happening here? Now, if you're running on a cluster with a really big data set, it might choose to actually distribute the processing of that amongst multiple computers, or multiple tasks at least. It might be running different processes or different containers on the same PCs, the same computers, or it might actually distribute them out amongst multiple computers. Kind of depends on how big the data is, how complicated the job is, and whatnot. So let's fabricate a little example here and say that MapReduce and Hadoop actually decide to distribute this out amongst, let's say, 3 nodes for mapping. So coming in, our data set might get chopped up into 3 parts. And it might actually send off the first couple of lines off to one node for processing, and the next few lines to a second node, and the next few lines to a third node. Now, in reality, it would be processing much more than just 2 or 3 lines on a given node, but scale this up to the idea of big data and you get the concept. Basically, it will carve up your input data into different partitions and then assign each node to a partition to process. So the thing about mapping is that it doesn't need to know about any of the other lines, right? So it's very easy to parallelize that operation. I can have a chunk of your input data being mapped on one computer while another chunk is being mapped at the same time on another computer. And all Hadoop has to do is keep track of when it's all done, right? So after that, that gives us an opportunity to distribute the processing of our mapping, of transforming the data, extracting the information we care about, and building these key value pairs. The next step is the shuffle and sort operation. And you can see how that could get a little bit dicey, right? Because you might actually have information for the same keys on multiple machines. And also those all have to be gathered together and sent to a specific key that will be sent to a specific reducer later on. So you can see that, we have ratings from user ID 196 spread across 2 different nodes here, and those both need to get aggregated together as part of the shuffle and sort operation. Now, the good news, again, is that MapReduce does this for you. You don't have to write any code for this to happen. It's just kind of magic. And the way it happens is a little bit more complicated than just, sending stuff all over the network willy-nilly. That wouldn't be very efficient. Instead, it uses sort of a series of merge steps to do, basically a merge sort of all this information as it funnels down to the reducer stage. But conceptually, you can think of it as things getting shuffled around and sorted. It's just using some tricks to actually make that more efficient. So at that point, things get sent to different reducers. And again, reducers can also be run in parallel. So each reducer might be responsible, each node might be responsible for reducing a given set of keys. So in this fabricated example here, I have 2 reducers. One's being fed data for user IDs 166 and 186, while my other reducer is being fed data for users 196 and 244. So again, for a given key, all the information that key needs is given to the reducer. So we can actually reduce different keys in parallel across different computers as well. At the end of the day, we get our final result, which would be streamed back to our client node. So in a nutshell, that's basically how MapReduce can distribute a job across an entire cluster. The mapping stage can be split up across different computers, where each computer receives a different chunk of the input data. And after the shuffle and sort operation, you can have different computers responsible for different sets of keys while reducing them. So what's happening under the hood here? So what's the anatomy of a MapReduce job? So you actually kick off your job from a client node. Some terminal prompt somewhere that you have open is actually kicking off this MapReduce job somewhere on a PC on your cluster, right? And the first thing that happens is that it goes and talks to the Yarn resource manager. Now, Yarn, remember, is yet another resource negotiator. It's another core piece of Hadoop, and it's what manages what gets run on which machines, okay? So it's keeping track of what machines in my cluster are available, which ones have capacity, and so on and so forth. So it talks to the resource manager and says, hey, I want to kick off a MapReduce job. And while it's doing that, it's also copying any data that it needs to copy to HDFS, or whatever distributed file system I want to use for this task. So it might need to copy some data up to be accessible by all of these different nodes that might be processing that data later on. So the next thing that happens is a MapReduce application master gets spun up. And this is running under what we call a node manager. So basically everything that's running MapReduce stuff is being managed by something called a node manager that just keeps track of what this node is doing. Is it up? Is it actually operating? Stuff like that. So the application master is now responsible for keeping an eye on all the different individual map and reduce tasks. And it works with the resource manager to actually distribute that work across your cluster. So let's imagine that we have two different machines in our cluster here, apart from our resource manager. And maybe this one's running a map task and another map task. These both might be running under a different container, a different JVM, but they're still managed by the same node manager, which talks to our application master and keeps track of what's running where. And we might have a second machine running a reduce task or something later on, and that might have its own node manager as well, all working in concert to keep track of what's up and what's not. And while these things are mapping and reducing stuff, it's talking to our HDFS cluster to actually receive the data that it needs to process and output the data results that it has at the end, okay? So at a high level, that's what's going on. You kick things off from a client node. There's a resource manager that's keeping track of all the different computers and what has availability. And then you have an application master responsible for keeping an eye on all of your tasks. And these node managers are keeping an eye on the individual PCs as a whole. And they all talk to our data on our HDFS cluster. One other thing worth talking about is that when your resource manager decides where to actually launch a given mapper or a given reducer, it will try to actually make that run as close to the data as possible. So let's say I'm running a mapper for a given subset of our input data. Remember, in HDFS, that input data is going to be split up into blocks that are replicated across 2 or 3 or even more nodes across your cluster. So it's going to try to make sure that a mapper responsible for processing a given subset of your input data will actually be running on the same machine that contains a copy of those blocks that it needs whenever possible. And if that's not possible, it will try to make sure it's as close to it in the network as possible. So it does a lot of work to make sure that you're not sending stuff over the network when you don't have to. And that's part of what MapReduce does for you. Okay, so the key takeaway here really is just that as it's distributing your MapReduce work across a cluster, you can actually have multiple tasks running on the same actual physical computer, and you can have multiple physical computers that are all coordinated by your application master and the resource manager. So let's talk about mappers and reducers in more depth. We kind of hand-waved that they are just functions that do stuff, that map things and reduce things, but how does it actually work? Well, natively, MapReduce is written in Java. In fact, all of Hadoop is written in Java. So if you want to write native MapReduce applications, you would do so using the Java programming language and providing jar files that produce them, that have the mappers and reducers that you need. Now, given that a lot of people taking this course might not be familiar with Java and all the complexity that comes with that in terms of compiling stuff and making sure all the dependencies you need are in place, I don't want to go there in this class. So let's talk about streaming, which actually allows you to use MapReduce with other simpler languages such as Python, and that makes life a lot easier. So the idea behind streaming in MapReduce is that a map task can just kick off through standard input and standard output, talking to some other process that's happening that actually implements your mappers and reducers. So instead of writing your mapping and reducing functions in Java, you can actually write them in Python or really anything that can run as a process on one of your compute cluster nodes, and it can just use standard input and standard output to communicate with that process. So basically, let's say a mapper wants to run, it will send the input data on standard in and receive back the output key value pairs on standard out. So just like with any other Unix tool, your streaming process can process that data and produce the output that MapReduce needs. How do we handle failure? I'll talk about that in a little bit more depth because that is an important feature of MapReduce and Hadoop in general. So a lot of things can go wrong, and what MapReduce and Hadoop gives you is a reliable way of dealing with these sorts of failures. The downside of using big clusters of commodity PCs or commodity hardware is that since they're commodity, they tend to go down at times, and you need to deal with that. So there's a lot of different ways things can go wrong. Let's say your application master, the thing that's monitoring your worker tasks, finds an error from a worker task, or a worker task hangs. Well, the application master can monitor that and just restart it as needed, and it's actually smart enough to try to restart it on a different PC, a different computer, if it can. Well, what if the application master itself goes down? Is that a single point of failure? Well, not really. Remember that the application master is actually spun up by the resource manager. So if the application master itself goes down, Yarn, the yet another resource negotiator component of Hadoop can actually try to restart it as well. So if you ever heard the expression, who's watching the watchers? Well, in this case, Yarn, the resource manager, is watching the application master. What happens if a whole node goes down, if an entire PC or an entire computer on your cluster just bursts into flames? And that could even be the application master. Well, again, the resource manager will take note of that and will just try to restart it on some other PC whenever it can. So the beautiful thing is that since each computer is just processing some subset of your data, it's not that big of a deal to just kick off a new instance of that mapper or that reducer on some other node and just start over for that subset. You don't have to start all over, right? But the one thing that is a little bit scary is if the resource manager itself goes down. So if your resource manager goes down, you're kind of out of luck. But there is a way of dealing with that if you're really paranoid. And there's what we call high availability MapReduce, where you can actually use Zookeeper, which we talked about way back in Lecture 2, to actually maintain a hot standby resource manager. So basically, MapReduce can always talk to Zookeeper first to figure out where is my resource manager, and if one goes down, Zookeeper can automatically redirect to a second backup resource manager. So if you really cannot tolerate any failure at all on your Hadoop cluster, that is an option for you. All right, so that's how Hadoop works under the hood at a very high level. Obviously, there's a lot more depth we could talk about if we wanted to, but there's only so much we can cover in this section. We have touched on, most of the main points, though. The only things that we haven't really talked about are, let's see, counters. It's actually possible to maintain a shared count across the entire cluster from your MapReduce programs. Just tuck that in the back of your head in case you ever need it. And what else? Combiners. There's also a little optimization you can do to actually try to do a little bit of reduction on your mapper nodes, which saves a little bit of overhead later on in your job. So there are more advanced things you can do to optimize MapReduce jobs, but I don't want to get into it too much for a couple of reasons. First of all, if you want more depth, there are other courses that talk about MapReduce in much more depth, and books as well. But also, MapReduce isn't really used as much as it used to be. It's been largely superseded by technologies like Spark or higher level tools that actually let you issue SQL-style queries to your cluster, such as Hive. So MapReduce is still kind of one of the fundamental building blocks of Hadoop, so it's worth understanding, but in this day and age, there are probably better options for actually coding up jobs like this than going to MapReduce directly. So let's take a look at another real example next and actually get into some actual code in our next lecture and see how MapReduce actually works at a coding standpoint. We'll do that next.
team. Get in the car. I'm out. Need ammo. I'm out. Need ammo. Expired! Cover me! Dead!
Great. You're about to win.
The blue team is about to win. Expired! Killed! Half of the
Blue
match is
team
over,
victory.
and the blue team is in the lead. Reloading!
Team match. Let's go.
First point for the red team. Enemy down! No mercy! Dead! Cover me! Kill! Enemy down! Cover me! Clear! Watch out! Killing spree for the red team! The red team is in the lead. Killing spree for the red team. Enemy down! Clear! Reloading! Cover me! Reloading! Kill! Enemy down! Cover me! Clear! Watch out! Marked a location.
Be careful. You're losing the game.
The blue team doesn't have a lot of time left. Marked a location. Kill! Reloading!
Red team victory.